Hello everyone and welcome. I'm excited to have you here today. Our presentation is all about masonry. We'll explore the fundamentals, techniques, and importance of masonry work. Over the next few slides, we'll dive into what makes masonry a vital craft and how it shapes our built environment. So let's get started. Let's talk about masonry. Masonry refers to an assembly or a combination of small building units. These units can be made from a variety of materials like clay, shale, concrete, glass, gypsum, or stone. The key point here is that these units are set in mortar, which binds them together and provides stability. Masonry can consist entirely of hollow or solid units, and these are laid in close contact, or contiguously, with mortar in between. This process creates strong, durable structures that are fundamental in construction. Understanding masonry is essential because it highlights how different materials and construction techniques come together to form various building types. It's a core concept that ties into the overall theme of building methods and material choices in construction. Now, let's take a closer look at the advantages of masonry structures. First and foremost, they are incredibly strong in compression, which means they can bear a lot of weight vertically without cracking or failing. This makes them highly durable for various building needs. Additionally, masonry acts as a natural heat absorber, helping to resist temperature fluctuations and maintain a comfortable indoor environment. This thermal stability can contribute to energy efficiency as well. Another key benefit is that masonry walls are mostly maintenance-free. Unlike other materials that require frequent painting or sealing, these walls typically don't need much upkeep over time. They also offer excellent fire resistance because of their non-combustible nature, providing added safety for occupants. From an environmental perspective, masonry is quite friendly. It's a leading contributor to green building practices due to its low impact on the environment. Plus, it offers superior soundproofing compared to traditional materials like timber, effectively blocking out noise and creating a quieter indoor space. Economically speaking, masonry utilizes locally available materials and labor, which can help reduce construction costs and support local economies. Overall, these advantages make masonry a versatile, durable, and sustainable choice for many building projects. Let's take a closer look at some of the disadvantages of masonry structures. First, moisture absorption is a common issue. When it rains, the masonry can absorb water, which may lead to further problems down the line. Next, extreme weather conditions can cause significant damage, such as color deterioration. Frost damage, for example, can cause the surface materials to decolorize and degrade over time. Another important point is the structural strength. Masonry has relatively low tensile strength, meaning it doesn't handle stretching or bending very well, which can be a concern for stability. When it comes to large openings, like big doors or windows, masonry can pose challenges because it's not as flexible or easy to work around these spaces without additional support. Education also plays a role here. There's often a lack of specialized knowledge about proper masonry techniques, which can affect the quality and durability of the structures. And because masonry is quite heavy, constructing large buildings requires a very strong foundation. This not only increases costs, but also raises the risk of cracking and settlement over time. So, while masonry has many benefits, these disadvantages remind us of the importance of careful planning and understanding its limitations, especially when considering it for larger or more exposed structures. Let's explore some basic terms in masonry that are fundamental to understanding how walls are constructed. First, we have the course, which is simply a horizontal layer of bricks or stones laid together. Think of it as one row in the wall. Next, the bed is the lower surface of each brick or stone within a course. It's positioned perpendicular to the line of pressure, providing stability and support. Moving on, the backing refers to the unexposed wall surface, which is usually hidden behind the facing. The facing, on the other hand, is exposed to the weather. It's what you see on the outside of the wall and must be durable to withstand environmental elements. Between the facing and the backing, we have the harding. This is the material filling the space, giving the wall its strength and stability. Now, let's talk about joints. The bed joint is the horizontal joint between courses, while the perpend joint is the vertical joint between bricks within a course. Both are crucial for the overall integrity of the wall. When we refer to headers, we mean bricks that are laid with their length perpendicular to the face of the wall. This helps tie the wall together horizontally. Conversely, stretchers are bricks with their longest side parallel to the face of the wall, giving a different visual and structural effect. Finally, the term bond describes how individual brick units are tied together using mortar. It's the pattern or technique used to ensure the wall's stability and strength. Understanding these basic terms provides a solid foundation for grasping more complex masonry concepts later on. Let's go through some basic terms in masonry that are essential for understanding how bricks are handled and laid. First, we have the closer. A closer is a piece of brick that's cut in such a way that one long face remains uncut, which helps in adjusting the length of a wall or filling gaps. Moving on, the queen closer involves cutting the brick lengthwise, so it's half the size, often used at corners or openings. The king closer is a bit more complex. It involves cutting off a triangular piece between the center of one end and the center of the other long side, mainly for fitting bricks in tight spots or corners. Next, we have the bat, which is a brick cut across the width, usually to fit into smaller spaces or for pattern work. Then there's the soldier, laid vertically with the long, narrow side exposed, creating a strong, decorative appearance. Opposite to that is the sailor, also laid vertically but with the broad face exposed, giving a different visual effect. Lastly, there's the rowlock, which is laid on the long, narrow side with the short end of the brick exposed, typically used in window sills or parapets. Understanding these terms helps us grasp how different brick cuts and placements contribute to the overall strength, appearance, and efficiency of masonry work. Each term represents a specific way bricks are cut or laid to achieve particular structural or aesthetic goals. Let's take a moment to look at some of the basic terms in masonry. These key concepts are fundamental to understanding how masonry works and its significance. When we talk about masonry, we're referring to the craft of building with individual units, like bricks, stones, or blocks, and the mortar that holds them together. Knowing these terms helps us appreciate the skill and precision involved. For example, terms like course, which refers to a single row of masonry units, and bond, which describes how these units are arranged for strength and stability. These basics connect directly to the overall theme of craftsmanship and the importance of strong, well-designed structures. By understanding these foundational terms, we gain a deeper insight into the art and science of masonry. Let's take a closer look at construction technology. This is an area that has seen incredible advancements in recent years, and it's really transforming how we build. Key points to highlight include the adoption of innovative tools and techniques that increase efficiency, safety, and sustainability on construction sites. For example, Building Information Modeling, or BIM, allows us to create detailed digital representations of projects, helping us identify potential issues early and streamline collaboration. Additionally, the use of prefabrication and modular construction methods is gaining popularity because they can significantly speed up projects and improve quality control. Robotics and automation are also starting to play a role, handling tasks that are repetitive or hazardous for workers. All these technological developments are interconnected with our overall theme of improving construction processes and delivering better results. They not only enhance productivity, but also help us reduce waste and minimize environmental impact. So, in essence, construction technology is opening new horizons for the industry, making our projects smarter, safer, and more sustainable. Let's discuss some key aspects of construction technology, specifically focusing on brick masonry. First, the lap, or the overlapping of bricks, should be at least 1/4 of the brick length along the wall. This ensures proper bonding and strength. Across the thickness of the wall, the lap should be at least half a brick, which helps maintain stability and uniformity. Next, when laying bricks in alternate courses, the vertical joints should align along the same perpendicular line. This staggered pattern enhances the wall's strength and prevents continuous vertical joints, which can weaken the structure. All finished masonry walls need to be cured properly for at least 7 days. Proper curing is essential for the masonry to gain the desired strength and durability, preventing cracks and ensuring longevity. The mortar joints should be uniform in thickness, and this thickness should not exceed 13 millimeters in any case. Consistent joints contribute to the aesthetic appeal and structural integrity of the wall. Finally, the height of brick masonry constructed in 1 day should not exceed 1.5 meters. This guideline helps manage quality control, ensuring the mortar sets properly and that the work remains precise and stable throughout the construction process. By adhering to these principles, we ensure the durability, strength, and quality of brick masonry structures. Now, let's take a closer look at the different types of bonds used in brickwork. First, we have the stretcher bond, which is one of the most common and simplest types, where bricks are laid lengthwise with each row offset by half a brick. This creates a strong and visually appealing pattern. Next is the header bond, where bricks are laid with the short end facing out, providing a different aesthetic and structural benefit. Moving on, the English bond combines stretcher and header courses in an alternating pattern, offering both strength and a classic look. It's widely used in load-bearing walls. The Flemish bond, on the other hand, alternates stretchers and headers within each course, creating a more decorative appearance with a distinctive pattern. Facing bond is designed primarily for its visual appeal, often used where the outward appearance matters most. Brick-on-edge bond involves laying bricks on their narrow edge, which can be used for specific design effects or structural purposes. Raking bond introduces a diagonal pattern by staggering bricks at an angle, adding dynamism to the wall. Then there's the Dutch bond, which resembles the English bond but with a different pattern of alternating headers and stretchers, giving it a unique look. Zigzag bond, as the name suggests, creates a zigzag pattern, often for decorative purposes. Garden wall bond is a variation that emphasizes a more rustic, informal appearance, typically used in garden walls. Rat trap bond is a popular technique involving bricks laid with the hollow side facing out, which saves material and provides insulation. Each of these bonds serves a specific purpose, whether for strength, aesthetics, or efficiency, and understanding them helps us choose the right technique for any project. These variations are all part of the broader theme of how brickwork can be both functional and visually striking. Now, let's take a closer look at the different types of bond patterns, starting with the Flemish bond. As you can see in the figure, this pattern alternates headers and stretchers in each course, with each header overlapping the one below. It's known for its strength and aesthetic appeal, often used in decorative walls. Moving on to the English bond, which is also quite popular. In this pattern, a course of headers is followed by a course of stretchers, creating a very uniform and sturdy wall. The key distinction here is that Flemish bond emphasizes a more decorative, interlocking pattern, while English bond prioritizes strength and simplicity. Both of these bond types are essential in masonry work, depending on the structural and visual requirements of the project. Recognizing these patterns helps us understand how different bonds contribute to the durability and appearance of brick structures, tying back to our overall theme of building techniques and material efficiency. Let's take a closer look at the comparison between English and Flemish bonds. Starting with English bond, the headers and stretchers are laid in alternate courses, which means each layer alternates between headers and stretchers. This bond is known to be the strongest among the types of bonds, providing excellent structural integrity. It also gives a rough appearance, which can add a rustic or traditional charm to the wall. One key advantage is that there are no vertical joints running through the structure, which enhances stability. Additionally, this bond doesn't require special attention during construction, making the process smoother. The work progresses more quickly because of its straightforward pattern, and it tends to be more costly since no brick bats are used, and skilled labor isn't necessarily required. Moreover, less mortar is used compared to other bonds, which can be beneficial in certain contexts. Now, shifting to Flemish bond, the headers and stretchers are laid alternately in each course, meaning each row alternates the pattern. This bond is considered to provide a good appearance, especially for aesthetic purposes. However, it is comparatively less strong for walls thicker than 30 centimeters, which is an important consideration depending on the building requirements. In terms of structure, partly continuous vertical joints can appear, which might affect the overall strength. Unlike the English bond, this one requires more attention during construction because precise alignment is necessary. The progress of work is slower due to its complexity, and it is more economical because brick bats are used. However, skilled labor is needed for proper execution, and more mortar is used because of the use of brick bats. In conclusion, understanding these differences helps us choose the right bond depending on the structural needs, appearance, cost, and labor considerations for our project. Let's take a closer look at the rat trap bond. This is a specific type of bond structure that often comes up in discussions about debt management and financial strategies. The key idea here is that the bond's cash flow profile is designed in such a way that it can create a kind of financial trap. In essence, a rat trap bond typically involves a situation where the issuer has a way to refinance or roll over debt repeatedly, making it difficult for investors to predict or realize their returns. This setup can be problematic because it may obscure the true risk involved, especially for those holding the bonds long-term. It's important to understand that this kind of bond can be a tool for issuers to manage their debt more flexibly, but it also raises concerns about transparency and investor protection. Connecting this to our overall theme, the rat trap bond exemplifies how financial engineering can sometimes complicate the risk landscape. It highlights the need for careful analysis and regulation to ensure investors are aware of potential pitfalls. So, in our broader discussion, recognizing structures like the rat trap bond helps us appreciate the complexities of debt instruments and the importance of clarity and sound risk management in financial markets. Let's take a closer look at the rat trap bond. On the face of the masonry, you'll notice the shiner and rowlock bricks. These elements create a distinctive appearance and serve a specific structural purpose. The design effectively bridges the internal cavity of the wall, which is a key feature of this bond. One of the main advantages of this bond is the economical use of bricks, making it a cost-effective choice. The cavity inside the wall isn't just for show. It significantly improves thermal comfort inside the building by providing better insulation. This bond is versatile and is used in both load-bearing walls and thick partition walls, thanks to its strength and stability. To further enhance the structural integrity, steel reinforcements are often inserted, increasing the overall strength of the wall. Another benefit is that the cavity helps reduce the weight of the building, which can be crucial in certain construction scenarios. And of course, the aesthetic appeal of the rat trap bond makes it a popular choice, giving walls a pleasing and textured appearance. All of these features, cost efficiency, thermal performance, strength, reduced weight, and visual appeal, highlight why the rat trap bond is a smart and practical solution in modern masonry construction. Hollow concrete blocks are a popular building material, and for good reason. They are known for their versatility and strength, making them a common choice in construction. One of the key advantages is their lightweight nature compared to solid blocks, which makes handling and installation easier and faster. These blocks also provide excellent insulation properties, helping to improve energy efficiency in buildings. Plus, they have good soundproofing qualities, which is essential in many types of structures. When it comes to durability, hollow concrete blocks are resistant to pests, fire, and weather conditions, contributing to the longevity of the structures they're part of. It's important to note that their hollow design isn't just about reducing weight. It also allows for the placement of reinforcement and services like electrical wiring or plumbing within the cavities. This feature adds to their functionality and adaptability in various construction projects. Overall, hollow concrete blocks align well with sustainable building practices too, since they often incorporate recycled materials and can be designed to optimize material use. So, they really exemplify how modern construction combines practicality, efficiency, and environmental consciousness. Let's talk about the advantages of hollow concrete blocks. One of the key benefits is that these blocks require low maintenance, which makes them a practical choice for many construction projects. They are highly durable, meaning they can withstand the test of time and harsh environmental conditions. When it comes to construction speed, hollow blocks allow for faster building processes compared to traditional construction methods, helping to save time and labor costs. Another important point is their high tensile strength, which adds to the structural integrity of the building. Economically, they are very friendly and inexpensive, significantly reducing overall building costs. This cost efficiency is complemented by their ability to lower both labor and material expenses. Hollow concrete blocks also offer excellent acoustic properties, improving the sound insulation of a room, and they help maintain thermal balance, keeping indoor temperatures comfortable and reducing energy consumption. Plus, since they are resistant to high heat and water, they are suitable for various climates and environments. One great advantage is that they don't require plastering, which further cuts down on finishing costs and time. They have low water absorption compared to bricks, making them more durable and less prone to damage from moisture. Finally, a very versatile feature is that the voids within the blocks can be filled with other materials, allowing for customization based on specific structural or insulation needs. Overall, hollow concrete blocks are a smart, cost-effective, and durable choice for modern construction. Today, I want to introduce you to the concept of compressed earth blocks, which are an innovative and sustainable building material. These blocks are made by compressing soil, often with minimal additives, to create a durable and eco-friendly alternative to traditional bricks. The key advantage here is that they utilize readily available earth materials, reducing the need for manufactured bricks that consume more energy. Compressed earth blocks are particularly exciting because they promote sustainable construction practices. They lower the carbon footprint of building projects and help in reducing waste. Plus, they offer excellent thermal mass, which can contribute to energy efficiency in buildings. In the context of our overall theme, sustainable and resilient architecture, these blocks exemplify how we can harness simple, natural resources to create strong, affordable, and environmentally responsible structures. They truly embody the idea that building materials can be both functional and environmentally conscious. One of the key advantages of compressed earth blocks is their cost-effectiveness, especially when it comes to shipping. Since suitable soils are often available right at or near the construction site, transportation costs are significantly reduced. This local availability not only saves money, but also minimizes the environmental impact of transporting materials over long distances. Another important benefit is the uniformity of these blocks. They are manufactured to a consistent size, with true flat sides and 90-degree edges, which makes the building process much smoother and more precise. This predictability helps ensure higher quality construction and reduces waste. When it comes to safety and health, compressed earth blocks are completely natural and non-toxic. They don't contain chemicals or outgas, making them a healthier choice for occupants and the environment. Sound resistance is also a major feature, especially in high-density neighborhoods or areas close to industrial zones. These walls help to reduce noise pollution, creating more comfortable living or working spaces. Additionally, earthen walls are fire-resistant. They won't burn, which adds an extra layer of safety to any building. They're also insect-resistant because their dense, solid structure discourages pests and provides no food source. Finally, because these blocks are made from locally available soil, the overall transportation costs are reduced, making the entire building process more sustainable and economical. All these factors together highlight how compressed earth blocks are not only environmentally friendly, but also practical and cost-effective for various projects. Today, I want to talk about masonry as infill walls. Masonry is a common choice for infill because of its durability and aesthetic appeal. These walls are typically placed between structural elements like frames or beams to fill in gaps and provide additional stability. One of the key points is that masonry infill walls can significantly improve the overall performance of a building, especially in terms of fire resistance and sound insulation. However, it's important to remember that they are non-structural, meaning they don't carry the load of the building but work together with the structural frame. This makes their placement and connection details crucial to prevent issues like cracking or instability. Connecting these infill walls properly to the main structure ensures they perform their role effectively while maintaining the integrity of the entire building. So, understanding how masonry works as infill is essential for designing safe, durable, and efficient buildings. Let's talk about masonry as infill walls and how they behave under seismic loading. Infill walls made of masonry can cause some undesirable effects during earthquakes, such as the short column effect, the soft story effect, torsion, and even out-of-plane collapse. These issues can significantly impact the building's stability and safety. Now, in many cases, these infill walls are separated from the reinforced concrete frame. This separation means they don't interfere with the frame during lateral deformations, so all the lateral forces are carried solely by the bare RC frame. This is a common approach, especially in developing countries, where infills are built as non-structural elements. In this configuration, the infill walls are essentially part of the building, but don't contribute to the structural capacity. They don't help carry lateral loads. The entire lateral force in the building is managed by the RC frame alone, which simplifies the design but can have implications during seismic events. On the other hand, there's a different approach where infill walls are built as integral parts of the RC frame, and they're considered structural elements. In this case, their in-plane stiffness is taken into account during analysis, meaning we assess how they contribute to the building's overall lateral resistance. The forces calculated from this analysis influence the design of the RC frame members and joints, leading to a more integrated and potentially more seismic-resilient design. Connecting this back to our overall theme, understanding how infill walls are modeled and their influence on seismic behavior is crucial for designing safer, more resilient structures. Whether they're treated as non-structural or structural elements, each approach has different implications for performance during earthquakes. Reinforced masonry, folks, is a construction system where steel reinforcement is integrated into the masonry to enhance its strength and durability. This can be done in a couple of ways, either by embedding steel reinforcement directly into the mortar joints of the masonry units, or by placing steel bars in drilled holes, which are then filled with concrete or grout. This method significantly improves the load-bearing capacity and resistance to various stresses. Now, when we talk about reinforced masonry, there are three main types to keep in mind. First, we have reinforced hollow unit masonry, which involves using hollow blocks with reinforcement inserted to add strength. Next is reinforced grouted cavity masonry, where large cavities between masonry walls are filled with grout and reinforcement to create a sturdy, integrated structure. And finally, reinforced pocket-type walls, which are built with pockets or holes in the units that are filled with reinforcement and grout, providing additional stability. Connecting this to our overall theme, reinforced masonry is a vital advancement in construction technology. It allows us to build taller, more resilient structures with better load distribution and safety margins. Understanding these types helps us choose the right method for different building needs, ensuring our projects are both safe and efficient. Reinforced grouted cavity masonry is an interesting and effective construction technique. Essentially, it involves creating a cavity wall with a grout-filled space between two masonry widths. The key here is the reinforcement, typically steel bars or mesh, which are embedded within the grout. This reinforcement adds significant strength and stability to the wall. What makes this method particularly valuable is its ability to resist lateral loads, such as wind or seismic forces, and also improve overall ductility. The grout acts as a bonding agent, ensuring the reinforcement stays in place and enhances load transfer between the masonry units. When we connect this to the overall theme of durable and resilient structures, reinforced grouted cavity masonry stands out because it combines the traditional benefits of masonry with modern reinforcement techniques. It's a great example of how integrating different materials and methods can lead to safer, longer-lasting buildings. Reinforced pocket cavity masonry construction is a technique that really enhances the strength and durability of brick and block walls. Essentially, it involves creating a cavity wall with a reinforced section, which adds stability and helps resist various loads, including wind and seismic forces. This method is particularly useful in areas where structural integrity is critical. By incorporating reinforcement within the cavity, we can prevent cracking and improve the overall performance of the wall over time. It's a smart way to combine traditional masonry with modern reinforcement techniques, aligning perfectly with our goal of building safer, more resilient structures. This approach not only extends the lifespan of the wall, but also provides better resistance against environmental stresses, making it a valuable method in our construction toolkit. Now, let's take a closer look at the typical anchorages of reinforcing bars. When we're working with reinforced concrete, ensuring the bars are properly anchored is crucial for the structure's strength and durability. The key idea here is that the anchorage points are where the reinforcement is embedded or bent to transfer stresses effectively. These anchorage points can take various forms, such as straight bars embedded sufficiently into the concrete, hooked ends, or bends that help develop bond strength. The most important concept is that the length of embedment or the type of bend must be designed carefully to develop the full strength of the reinforcement. This is especially vital in tension zones, where the bars are primarily resisting pulling forces. Proper anchorage prevents slippage and ensures the load is transferred efficiently from the concrete to the reinforcement. Connecting this to our overall theme, understanding these anchorage details helps us design safer, more reliable structures that perform well under load. It's a fundamental aspect that influences the integrity and longevity of our concrete constructions. Unreinforced masonry buildings are particularly vulnerable during earthquakes. The key issue is that they are likely to sustain damage when shaking occurs. This is mainly because the mortar holding the bricks or stones together isn't strong enough to resist the forces generated during an earthquake. Without proper reinforcement, these walls can easily crack or crumble. Another critical point is the importance of anchorage, how well the walls are connected to the floors and the roof. If these connections are weak, the entire structure becomes unstable. Think of it this way: if the walls aren't securely attached, they can break apart or buckle under stress. These types of houses tend to be brittle and can break apart quite easily. During seismic activity, you might see walls fall away or buckle, leading to significant damage. This highlights the overall importance of retrofitting and strengthening masonry structures to improve their resilience against earthquakes. Unreinforced masonry, or URM, refers to structures built primarily with bricks or stones held together with mortar, without the use of steel reinforcement. These types of buildings are quite common historically, and in many regions around the world. One of the key issues with unreinforced masonry is its vulnerability during seismic events. Because there's no reinforcement to absorb and dissipate energy, these structures tend to perform poorly under earthquake shaking. They are prone to cracking, spalling, or even collapse in severe cases, which can pose serious safety risks. This is a critical point to understand because, as we look at building safety and retrofitting strategies, unreinforced masonry buildings often require special attention. Retrofitting can involve adding reinforcement or other techniques to improve their seismic resilience. Overall, recognizing the limitations of URM is essential when assessing the seismic vulnerability of existing structures and planning for safer, more resilient buildings in the future. Let's talk about confined masonry. In this system, the masonry walls are responsible for carrying the seismic loads, meaning they bear the forces generated during an earthquake. To support these walls, we use reinforced concrete around all four sides, creating a sort of cage that surrounds the masonry. This confinement is crucial both vertically and horizontally because it helps resist lateral forces from earthquakes as well as gravity loads from the structure itself. The key here is that the confining members, those reinforced concrete elements, are highly effective in several ways. First, They improve the overall stability and integrity of the masonry walls when faced with in-plane and out-of-plane earthquake forces. Second, they significantly increase the strength of the walls during seismic events, making the structure more resilient. And third, confinement reduces the brittleness of the masonry, which means the walls are less likely to crack catastrophically and can perform better during an earthquake. So, confinement isn't just about adding strength. It's about creating a more ductile, safer structure that can withstand seismic forces more effectively. This approach aligns perfectly with our overall goal of seismic-resistant design, ensuring buildings are safer and more durable in earthquake-prone areas. Let's take a closer look at confined masonry. The main structural components here include the masonry walls, which form the core of the structure. These walls are reinforced by confining elements such as tie beams and tie columns, which help improve stability and resistance to lateral forces. Additionally, the floor and roof slabs serve as the horizontal elements that distribute loads and provide rigidity. The plinth band is an important element at the base, helping to tie the walls together and prevent settlement or differential movement. Finally, the foundation anchors the entire structure to the ground, ensuring stability and transferring loads safely to the soil. Altogether, these components work in harmony to create a resilient and earthquake-resistant structure, emphasizing the importance of integration and proper design in confined masonry systems. Confined masonry is a construction technique that combines the use of load-bearing walls made of masonry units with reinforced concrete tie beams and columns. This method is particularly effective in seismic zones because it enhances the building's overall stability and resilience. The key idea here is that the masonry walls resist lateral forces, while the reinforced concrete elements help hold everything together and prevent failure during an earthquake. One of the main advantages of confined masonry is its cost-effectiveness and ease of construction, especially in developing regions where resources might be limited. It also offers good thermal and acoustic insulation properties, making it a practical choice for residential and commercial buildings. Connecting this to our overall theme, confined masonry exemplifies how thoughtful, localized construction techniques can improve safety and durability in vulnerable areas. It's a perfect illustration of integrating traditional building methods with modern reinforcement to meet the demands of seismic resilience. Today, I'll be introducing you to the codal provisions, focusing on their scope and application. When it comes to the structural design of walls, these provisions specifically cover unreinforced load-bearing and non-load-bearing walls. These walls are constructed using materials like solid or perforated burnt clay bricks and concrete blocks, which are common in many building practices. It's important to note that these provisions do not apply to walls built with mud mortars, so if you're working with traditional or earthen materials, different guidelines would be necessary. Understanding these distinctions helps ensure we're applying the correct standards for safety and durability in our projects. This scope clarifies which types of walls are covered under these provisions, aligning with the overall goal of promoting sound structural design. Walls are arguably the most essential component of any building. They essentially enclose or divide the space within a structure, giving it its shape and defining its function. But beyond just enclosing space, walls also serve important practical purposes. They provide privacy for the occupants, and they offer security and protection against external elements like heat, rain, and cold. When we design walls, there are several key qualities we need to focus on. First, strength and stability are crucial, because a wall must be able to bear loads and withstand environmental forces. Weather resistance and thermal insulation are also vital. These help keep the interior comfortable regardless of outside conditions. Durability and fire resistance are equally important to ensure the wall lasts over time and provides safety in case of fire. Additionally, sound insulation plays a significant role, especially in urban environments or in buildings where noise control is necessary. Ultimately, a well-designed wall balances all these factors, supporting the overall integrity, safety, and comfort of the building. It's fascinating how this single element touches so many aspects of building performance and occupant well-being. Let's start by understanding what walls are in the context of structural elements. Walls are vertical load-bearing members, and an important feature is that their width or length exceeds 4 times their thickness. This ratio helps us distinguish walls that are primarily designed to carry loads from other types of vertical elements. Now, there's also a specific term for isolated vertical load-bearing members, where the width does not exceed 4 times the thickness. These are called columns. Columns are typically used to support loads at specific points, like in beams or arches. Moving on to the different types of walls, we have load-bearing walls. These are crucial because they are designed to carry not just their own weight, but also any superimposed loads, such as floors, roofs, or additional structures above. On the other hand, non-load-bearing walls are primarily designed to carry only their own weight. They don't support floors or roofs, but serve other functions like dividing spaces or providing privacy. Understanding these distinctions is key to designing safe and efficient structures. Load-bearing walls are integral to the overall stability, while non-load-bearing walls help define the interior layout without contributing to the building's structural support. So, recognizing the purpose and characteristics of each helps us in planning and constructing buildings that are both functional and safe. Let's take a closer look at the different types of walls and their roles within building structures. First, we have the partition wall, which is typically a thin internal wall used to divide spaces within a building. It's not load-bearing, but it helps organize and separate different areas. Next, the internal wall, which is a load-bearing partition wall. This means it supports some of the building's weight, contributing to the overall stability. Then there's the panel wall, usually an external wall that's non-load-bearing and related to the frame structure. Think of it as a facade that protects and insulates the building without carrying the main loads. Moving on, the party wall is a special kind of wall that separates adjoining buildings. Its load-bearing capacity can vary. Sometimes it supports part of the structure, sometimes not. It's essential in shared property boundaries. The separating wall, on the other hand, divides different occupancies within the same building, providing privacy and fire separation. Now, the curtain wall is quite interesting. It's a self-supporting external wall that doesn't carry any vertical loads, but must withstand lateral forces like wind or seismic activity. This type of wall is common in modern high-rise buildings, giving a sleek exterior while being independent of the main structural framework. Finally, we have cross walls. These are load-bearing internal walls that run perpendicular to the length of the building. They carry all the internal loads, helping to distribute weight efficiently across the structure. Understanding these different wall types is crucial because each serves a specific purpose, whether for support, separation, or aesthetics, and plays a vital role in the overall stability and functionality of a building. When we talk about load-bearing walls, the most common type you'll encounter is solid masonry walls. These are straightforward and widely used because of their strength and durability, although they can have openings like doors or windows. Then we have cavity walls, which are a bit more complex but offer some important advantages. A cavity wall consists of 2 separate leaves, or layers, of masonry units. These leaves are separated by a cavity, which can either be kept continuous or filled with insulating material. To ensure that both leaves work together as a single structural unit, metal ties or bonding units are used to connect them securely. Understanding the difference between solid walls and cavity walls is crucial because it impacts how load is transferred and how well the structure can handle environmental factors like insulation and moisture. Both types play a vital role in construction, and choosing between them depends on the specific needs of the building and the overall design considerations. Let's take a closer look at load-bearing walls, starting with faced walls. These are walls where the facing and backing are made from 2 different materials, but they're bonded together so they act as a single unit under load. This bonding ensures that the wall can effectively carry structural loads without the facing detaching from the backing. Now, moving on to veneered walls. In these walls, the facing is attached to the backing, but there's no strong bonding to make them act together structurally. Think of it more like a decorative layer that's attached for appearance, but it doesn't contribute to the structural load-bearing capacity. Understanding these distinctions is important because it influences how we design and construct walls to ensure they perform safely and efficiently under various loads. Recognizing whether a wall is faced or veneered helps us determine its load-bearing capability and how it fits into the overall structural system. Let's talk about some key design considerations for masonry structures. First, it's important to understand that these structures gain stability mainly from the supports they receive from cross walls, floors, roofs, and other elements. These components work together to hold everything in place and ensure the structure remains stable over time. Another critical point is that the structure should be planned so that the eccentricity of loading on the members is kept as small as possible. Now, eccentricity refers to the offset of the load from the center of the element, which can cause bending or additional stresses. Minimizing this offset helps distribute forces more evenly, reducing potential weaknesses or failure points. By focusing on these aspects, we're ensuring that the overall design promotes strength and durability. Remember, a well-thought-out structure not only stands firm, but also efficiently resists various forces acting upon it. This is essential when aiming for safe and lasting masonry constructions. When selecting mortar for masonry work, there are a few key factors we need to consider. First and foremost is the workability of the mortar, which affects how easy it is to apply and how well it bonds the bricks or blocks together. Strength is also crucial, though interestingly, the mortar's strength should generally not exceed that of the masonry units themselves. This ensures that the units carry the load, not the mortar. Water retention is another important point, as good water retention helps the mortar bond properly and prevents issues like cracking or weak joints. Additionally, low drying shrinkage is desirable to minimize cracking as the mortar dries. Now, looking at the table, we see different mortar types assigned based on the strength of the masonry units. For units with strength below 5 M2, we use M2 mortar, which is relatively low strength. For units between 5 and 14.9 M2, M1 mortar is suitable. When the units are between 15 and 24.9 M2, we move to H2 mortar, indicating a medium-high strength. And for units with strength of 25 M2 or above, H1 mortar is appropriate, offering high strength. It's also helpful to remember what these letters stand for, H, M, and L, indicating high, medium, and low strength, respectively. This classification helps us choose the right mortar to match the strength of the masonry units, ensuring durability and stability in the structure. So, choosing the correct mortar isn't just about adhering bricks, it's about optimizing the entire system for strength, longevity, and performance. Let's continue with some important considerations for stability. When we talk about lateral support, we're essentially discussing how the walls are supported against horizontal forces. These forces can be transmitted either vertically by floors and roofs at certain intervals, pushing horizontal forces to cross walls, and then down to the foundation. Alternatively, they can be supported horizontally by cross walls or piers, which transfer these forces directly to the foundation. Now, why is this lateral support so crucial? Well, it serves two main functions. First, it helps resist the horizontal forces that could cause the structure to overturn. Think of it as preventing the building from tipping over in strong winds or seismic activities. Second, lateral support limits the slenderness ratio of the masonry elements, meaning it prevents these elements from becoming too tall and thin, which could lead to buckling and failure. When we evaluate if a wall has adequate lateral support, we look at a couple of key criteria. 1. The supports must be capable of resisting the combined lateral forces acting on the wall. This includes simple static reactions, like the support pushing back against the load. And 2, the lateral support should be able to handle at least 2.5% of the total vertical load that the wall or column is designed to carry at that support point. By ensuring these support conditions are met, we make sure the structure remains stable under various loads and prevents potential failure modes. This is a vital aspect of structural design that ties into the overall safety and durability of the building. Let's now consider the effective height of a load-bearing wall. The key idea here is that this height isn't just a simple measurement. It depends quite a bit on the relative stiffness of the various structural elements connected to the wall. Basically, how well these elements resist deformation influences the wall's effective height. In addition to that, the efficiency of the connections plays a crucial role. Strong, well-designed connections ensure that the load is transferred properly and the structure behaves as intended. It's also important to remember that walls can be stiffened by other structural components like floors, roofs, or cross walls. These elements help distribute loads and improve overall stability. So, when we're designing or evaluating a building, understanding these factors helps us ensure that the load-bearing walls will perform effectively under various loads and conditions. This ties directly into our overall goal of creating safe, durable, and efficient structures. Let's talk about the slenderness ratio, or SR for short. Essentially, it's the ratio of the effective height or length of a wall to its effective thickness, whichever is less. This ratio helps us assess the stability and potential buckling of walls under load. For load-bearing columns, it's important to note that the slenderness ratio should not exceed 12. Keeping this ratio in check ensures safety and stability in our structures. Now, when it comes to load-bearing walls, the maximum slenderness ratio varies based on the number of stories and the type of mortar used. For walls in buildings up to 2 stories, the maximum SR is 27 if you're using Portland cement in the mortar, and it's slightly lower at 20 if you're using mortar lime. If the building exceeds 2 stories, the maximum SR drops to 27 for Portland cement mortar, but only 13 with mortar lime. This reduction helps prevent excessive slenderness that could compromise the wall's stability. All of these values are referenced from Table 7 in IS 19-051987, which provides standardized guidelines for such design considerations. Understanding these ratios and limits is crucial for designing safe, durable walls that can withstand their loads without buckling or failing over time. Let's talk about the structural design aspect. First, the general principle here is to analyze the structure using accepted mechanics principles. This is essential to ensure that the structure will function safely and properly during its service life. We need to make sure all components can withstand the most adverse load combinations they might face, not just during construction, but also afterward. When we consider design loads, we include several key factors. Dead loads, which are the weight of the walls, columns, floors, and roofs, are fundamental. Then we have live loads on the floors and roofs, which we calculate using IS 875 Part 2. These represent the variable loads, like people, furniture, or moving equipment. Wind loads are also critical, especially on walls and sloping roofs, as they can exert significant pressure or suction forces. And finally, seismic forces come into play, but their application depends on the seismic zone. For zones I and II, sometimes seismic forces are considered less critical, but for zones III, IV, and V, it's essential to adopt seismic design considerations. All these factors combined help us ensure that the structure remains safe, stable, and durable throughout its use. Now, let's continue with the structural design considerations, focusing on load dispersion. When we talk about the angle of dispersion of vertical loads on walls, it's important to keep it within a practical range, specifically, not more than 30 degrees from the vertical. This helps ensure that the load transfer remains efficient and that the walls are not subjected to excessive lateral forces. Additionally, we need to account for the arching action, especially in well-bonded walls that are supported on lintels and beams. This arching effect can significantly influence how loads are distributed across the structure, providing additional stability and strength. Recognizing this behavior allows us to design more resilient walls that effectively manage the load transfer, ultimately supporting the overall integrity of the building. So, in summary, understanding and properly designing for load dispersion and arching action are key to creating safe, durable structures that perform well under various loads. Let's continue by discussing the permissible stresses in structural design. First, we'll look at the permissible compressive stress. This is calculated using the formula FB multiplied by Ks, Ka, and Ks again, which accounts for different factors affecting the material. FB, which is the basic compressive stress, depends on the type and strength of the masonry units, as well as the mortar mix. You can find the values for FB in Table 8. Then, we have the stress reduction factor, Ks, which depends on the slenderness ratio, SR, and the eccentricity of the loading, as shown in Table 9. Next is the area reduction factor, Ka. This adjusts for the size of the area being considered, and it's calculated as 0.7 plus 1.5 times A, where A is the area in square meters. We also need to consider shape reduction factors, which again influence the permissible stresses depending on the shape of the element. Moving on to the permissible tensile stress, it's generally quite limited, given the material's weaker tensile capacity. Lastly, for shear stress, we have a formula. Fa equals 0.1 plus F divided by 6, which should not exceed 0.5 N squared. Here, Fa is the permissible shear stress, and F is the compressive stress due to dead load. All these factors together help us ensure that the structure remains safe and durable under various loading conditions, aligning with our overall goal of sound structural design. Let's talk about wall openings and their effect on structures. When we introduce openings into walls, especially URM walls, they tend to reduce the lateral strength of those walls. That means the walls become less capable of resisting forces like wind or seismic loads. To manage this, it's important that openings are kept small and are placed centrally within the wall. By doing so, we help maintain the wall's overall stability. Now, when considering the total length of these openings, there are specific guidelines. For one-story buildings, the total length of openings should not exceed half the length of the wall, and for two-story buildings, this limit is reduced to 1/3. These ratios are critical because they help us balance functionality, like doors and windows, with structural integrity. Remember, the goal here is to ensure that while we provide necessary openings for doors and windows, we're not compromising the building's overall strength and safety. Keeping these key points in mind allows us to design more resilient structures that perform well under various loads. Let's wrap up by referencing NBC 109, which highlights some of the key takeaways we've discussed today. This resource underscores the importance of thorough planning, clear communication, and continuous improvement in our processes. Remember, the overall theme of this presentation has been about building a strong foundation for success through strategic approaches. By applying these principles, we can ensure better outcomes and more effective teamwork. Thank you all for your attention and engagement throughout this session.